Solutions to some calculus problems from section 10.7 is our first foray into Taylor polynomials. In numbers 7 through 12, they want us to find the Maclaurin polynomial, which just means Taylor polynomial at x sub 0 equals 0. That's what that means. Those are the easiest ones to find. We'll do those a lot of the time, not always, but that's what that means. And I'm going to go ahead and write out, we know that the Taylor polynomial, the nth Taylor polynomial, is equal to the function evaluated at 0 in this case, right, plus the derivative at 0 times x. And if you're thinking like, well, that's x minus 0, right? All those little factors, all the minus x sub zeros, those are all 0. Times x squared over 2 factorial. And then there's the 3 term, third derivative, times x cubed over 3 factorial, fourth derivative, x is x to the 4th over 4 factorial. And if we wanted to find the nth one, we would just go dot, 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 all the way up to the nth derivative times x to the n over n factorial. So that's what that nth Taylor polynomial would look like at x sub 0 equals 0. And that's sometimes called the Maclaurin polynomial for that special case where we're doing it at 0. And right? I'm sorry, these should be zeros. I'm evaluating it at 0. Knew something looked wrong there. Right, it's all the derivatives evaluated at 0. Right, of course these aren't zeros, these are the variable x. If those were all zeros, then the whole thing would just be equal to f of 0, and that's just a horizontal line. That ain't nothing we're interested in. All right, so let's take that for a spin. In the first one, we're going to do it for the function e to the negative x. So if I'm going to do the book's asking here for the 0, 1, 2, 3, and 4, I'm just going to do the fourth one, and then if we want to know the 0th one, we just do that, and then there's the first one, and then there's the second one, and third one, and so on. So if you find the fourth one, you really have all the other ones. You just have to cover up some terms. And if we're going to do that fourth one, we need to find 4 derivatives of this. And with the e to the x type function, that's pretty easy. Using the chain rule, a negative would pop out, so that's going to be negative e to the negative x, and then positive e to the negative x, because another negative pops out, and it's going to alternate back and forth like that. And then we just need to cook it up with this recipe here. So if you want to, you can add to your table here. So what's f of 0? F of 0 is what you get when you plug 0 into this. That's e to the 0 power, which is 1. And f prime of 0 would be, well, e to the 0 is still 1, but I have a negative here, so that's negative 1. And then we're back to positive 1, and then back to negative 1, and then positive 1 again. Right, so that's all my derivatives. And that's all I need, right? The rest of it's just the recipe here, right? These are the things that I need. So the fourth Taylor polynomial would be 1, and this is negative 1, so that'd be minus x, and this is positive 1, so it'd be plus x squared over 2 factorial, and then this is negative 1, so minus x cubed over 3 factorial plus x to the 4th over 4 factorial. And then they're asking me to write what is the nth one, the nth Maclaurin polynomial, in sigma notation. And let's see if we can do that. This is a very important skill for us here. Well, the signs are flipping, so I know I have a sign flipper. But negative 1 to the n. I might have to put a plus 1 here if the signs aren't right. I'll figure that out once I decide where I'm going to start. And then it looks like I have x to the n power. It goes 0, 1, 2, so maybe I'll start at 0, right? X to the 0, x to the 1, x squared, and so on. And then over the same factorial as what we have here, so n factorial. And do remember that 0 factorial is equal to 1 by definition. So if I start at 0, that's going to give me the right first term, and it'll give me the right first sign too, so I don't need the plus 1 there. So for n equals 0 up to, and they said the nth one, so maybe I should have made those all k's if they want to know up to n, or maybe I'll just do this instead, up to k. So there's the kth Taylor polynomial. Right? And if you plugged in the numbers from 0 up to k, you would get this. For example, if you plugged in 4 here, you get exactly that. So engineering these things is definitely an important skill for us. Number 8, we have the function e to the ax. So what do the derivatives of that look like? Well, when I take the derivative of this by the chain rule, an a is going to pop out, and then another one, and then another one, oops, and then another one. So every time the chain rule pops another a out. And then if I want to know what those are equal to at 0, what's f of 0, what's f prime of 0, what's f double prime of 0, what's f triple prime of 0, and what's f quadruple prime of 0. That's what I get when I plug 0 in for these. So e to the 0 is 1. This part is going to become 1 for every one of these. So I just get this part in front. And then I just need to cook this thing up with our recipe here. So f of 0 is 1 plus, that's a, times x, plus I have a squared times x squared over 2 factorial, plus a cubed times x cubed over 3 factorial, plus a to the 4th times x to the 4th over 4 factorial. Right? Just plugging all of those in here. Now, can I write in sigma notation? So we've got a little practice from the last one. It's not flipping signs, so I don't need a sign flipper. I have x to the 1, 2, 3, 4, so x to the n power. And every time I have an n there, I have an n factorial on the bottom. And I also have an a to the n power, whatever power shows up here. And where do I want to start? It looks like I want to start with no x's at all, so I want to start at n equals 0. I'm going to do, too late. I guess I'll do up to k again. I just can't use the same letter there. So this is actually for the kth polynomial. And that's what it looks like in summation notation. Number 9. Got this time the cosine of pi x. So f of x is equal to cosine of pi x. Derivatives of sine and cosine are easy. I guess all derivatives are pretty easy for us now, right? Those were the days. All we had to do was take derivatives. Derivative of cosine is negative sine, but the chain rule is going to pop out a pi, so I'll do that. And then the derivative of negative sine is negative cosine, and another pi is going to pop out. The chain rule again, that's going to happen every time. And derivative of negative cosine is positive sine, pi cubed times the sine of pi x, and the derivative of sine is cosine. Another pi pops out. And then at 0, maybe I can do this. At x equals 0, and then just say this is equal to. When I plug in 0 here, I get cosine of 0, which is 1. When I plug 0 in here, that's sine of 0, which is 0, so it doesn't matter what I'm multiplying by. When I plug the 0 in here, cosine of pi is 1, so I get negative pi squared. Sine of 0 is 0, and cosine of 0 is 1. I get pi to the 4th. Okay, so let's cook it up. So the fourth Taylor polynomial, or Maclaurin polynomial if you want, is equal to 1. And then there's no x term. The coefficient of the x term would be 0, so that's going to get knocked out. And minus pi squared times the x squared over 2 factorial term. The cubic term is going to get knocked out by that 0, and plus pi to the 4th times x to the 4th over 4 factorial. And let's see if we can do the summation notation for that. This time I'll try to write it. I'll do it from k equals up to n, so we can really call it the nth one. It really doesn't matter much what you call those as long as you're consistent. So it looks like we only have the even terms. So even terms are represented by 2k, 2 times a number. So it looks like in all the terms I have pi to the 2k times x to the even number 2k, same one, over same number 2k factorial. But the signs are flipping also, so I need a negative 1 to the k for my sign flipper. Now, where do I need to start to get 1 as the first term? I need all these things just to turn into 1s. So I'm going to start at k equals 0. And if I start at k equals 0, then my first term will be positive. So that checks out there. It takes a little bit of practice to get those. And the even odd thing is very important to know how to do, but we'll have lots of practice with that. All right. Number 10. This time we have sine of pi x. So f of x is equal to sine of pi x. Derivative, cosine, sorry I forgot about the pi there from the chain rule, pi times the cosine of pi x. That's the derivative, and then the second derivative would be negative pi squared times the sine of pi x, and the third derivative would be equal to negative pi cubed times the cosine of pi x, and then the fourth derivative would be equal to pi to the 4th times the sine of pi x. Right? And it's worth maybe commenting on the fact that when you do these derivatives of sine and cosine, you get positive, positive, negative, negative, positive, positive. That always happens like that. So let's cook this thing up. Oh, sorry, not yet. What are these equal to at x equals 0? When x equals 0, the sine of 0 is 0. Cosine of 0 is 1, so that would be pi, and then that's 0 again, and then negative pi cubed, and then 0 again. So it looks like the fourth degree polynomial only has two terms here, only has the first and third terms. So that's going to be pi times x minus pi cubed times x cubed over 3 factorial. And that's it. The other one's all the even terms. And the very first one, that's like the 0th term, so that's even. They all got knocked out to 0. In summation notation, now we have odd terms only. So how do we make odd terms? Well, we can do x to the 2k plus 1. 2k is an even number, so if you take even numbers and add 1 to them, you get odd numbers. And then I need to raise pi to that same power, 2k plus 1. And on the bottom, I have the same 2k plus 1 factorial. And the signs are flipping, so I also need a sign flipper. And what do I need to start with here? I want my first term to be pi to the first, x to the first. So that would be plugging in 0 for k to make that happen. So see, these actually start at 0 a lot of the time. And then if I want the nth one, go up to n. So that's what that looks like. And that's how we do odd numbers. 2k plus 1 or 2n plus 1 if you're using n's. Number 11. F of x is equal to the natural log of 1 plus x. When we do our derivatives, this is not quite as easy as it was before. So the derivative of natural log is 1 over, and I'm going to write that as 1 over 1 plus x, and times the derivative of what's inside. The derivative of what's inside is just 1. So that's my derivative there. The second derivative, the derivative of something to the negative 1 is negative that thing to the negative 2 times the derivative of what's inside, which is just 1. Third derivative, multiply, just using the power rule here, so negative 2 times the negative that's there will give me 2. There's a 1 plus x to the negative 3. And then fourth derivative is negative 6 times 1 plus x to the negative 4. Let's evaluate these things at x equals 0. The natural log of 1 is 0. 1 plus 0 to the negative 1 is 1. 1 plus 0 to the negative 2 is 1 with a negative sign there. And 1 plus, you can maybe get the idea that 1 plus 0 to whatever power is always going to be 1. So I'm just going to get these numbers 2 and negative 6. And notice that negative 6 is 3 factorial. Right? That came from 2, and then it could multiply by 3. If we did it again, it would be 24, right? 4 times 6 would give me a 24. All right, so let's cook this sucker up. The very first term is 0, and then the x term is 1 times x, and minus 1 times x squared over 2 factorial, which is 2, plus third term is 2 times x cubed over 3 factorial, and minus 6, which is the same as 3 factorial, times x to the 4th over 4 factorial. That one's a little different, so I think that's worth pausing and making sure you understand in case you're watching this at hyperspeed or something. I'm going to simplify this one. That's x squared over 2. 3 factorial is 3 times 2 times 1, so the 2 cancels out, and that just turns into, that would just be x cubed over 3. And then 3 factorial on the top, 4 factorial on the bottom, just leaves a 4 on the bottom. So I think that helps us see what's going on here. And in sigma notation, looks like I need x to the k power. I need a sign flipper, and then divided by the same as that power, which is k. Now here in this one, it looks like I would like to start at 1. K equals 1. And if I put a 1 in here, I'd get a negative 1, but I want to start with a positive term, so that needs to be k plus 1. So the nth Taylor polynomial for the natural log of x of 1 plus x is that. And if you plug 4 in for n, you get this. Number 12. I have the function 1 over 1 plus x. And I'm going to, for the purposes of taking derivatives, think of it like that. And notice that that's the same as this. So we really kind of just did this. We're just one step down the road. So the first derivative is negative 1 to the 1 plus times 1 plus x to the negative 2. Just power rule. Just using the power rule. That's all. Third derivative, negative 3 times that. That's negative 3 times 2, which is 3, it's 6, but that's the same as 3 factorial, times 1 plus x to the negative 4. And the fourth derivative is negative 4 times negative 3 factorial is 4 factorial. So 1 plus 5 to the negative 5th. Right? All right, let's see what it looks like here. Oh, nope, not yet, sorry. And then at x equals 0, what are all these equal to? Well, all these things in parentheses are going to equal 1. Right, so that's just equal to 1, and then this is equal to negative 1, and then this is just equal to 2. That's equal to negative 3 factorial, and then that's equal to that. So, cook this thing up. First term, f of 0 is 1. Next term, minus x. Next term. And if I'm going a little bit too fast in terms of how I'm following the recipe, I would definitely, pause the video, have the recipe right there so you can see where this is coming from. But it's just these coefficients times the x squared over 2 factorial, x cubed over 3 factorial, x to the 4th over 4 factorial, and so on. So this is 2 times x squared over 2 factorial minus 3 factorial times x cubed over 3 factorial plus 4 factorial times x to the 4th over 4 factorial. And that definitely wants to be simplified, doesn't it? 1 minus x plus the 2's cancel plus x squared minus the 3 factorials cancel. 4 factorials cancel. That just gives me this. And the summation for that is equal to k equals something to n. So I've got x to the k power. The signs are flipping. We'll see if we need a plus 1 there or not. And then on the bottom I don't have anything, do I? So it's just that. All the stuff on the bottom canceled out. Now where do I want to start? I want to start with a 1. That's x to the 0. And if I start with a 0, I get a positive first term, so it's just that. And I'm going to go ahead and point out to you here, if you look at this, series. This is, well, actually I'm not going to point it out here, but let me just suggest this, if you care to think about it at this point. This looks like a geometric series. So I want you to think about the sum of a geometric series and what that sum would look like if you plugged in the first term in the R, what the sum of that geometric series would look like. We'll come back to that and see that some more later. Let's see, I'm kind of tempted to stop this video here and then maybe make another one that has the rest of the problems. So, it was false advertising that it would be all of these, but I think maybe I will do that, and I'll leave these problems for a second video. That's a good 25 minutes, and maybe that's enough for now.